So the next part of the experiments in control systems lab are lead and lag compensator. Already in the very first chapter of advanced control system, you have come across what is lead compensator, what is lag compensator, and what exactly the role of lead and lag compensator. So the main objective in the control system lab is to study the frequency response of lead compensator and lag compensator. Today I am going to explain how to achieve the frequency response of lag compensator. So let's move to the derivation part. This is the electrical system for the lead compensator, which comprises of parallel combination of R and C, and which is further connected to R2 in series. And we are applying the input here and we are measuring the output across R2. So initially, to obtain the frequency response of this lead compensator is the main objective of this work. So before that, you must understand what is frequency response. Frequency response is nothing but the board plot which comprises of magnitude versus frequency and phase shift versus frequency. So it is a theoretical approach and you are going to verify the same thing experimentally here. So to construct the board plot, what you need is the transfer function. So you should derive the transfer function here. So first you simplify this parallel combination. I am considering that as an impedance Z1 of S is R1 parallel with 1 over AC, and this is what you are going to get. And R2 I am considering it as Z2. So obviously if you replace this one by Z1 and if you consider this as Z2, it is nothing but a divider network. So V0 is equal to V in into Z2 divided by Z1 plus Z2, and substitute the expressions of Z1 and Z2 in this equation, and then if you simplify, this is what the equation you are going to get. So here I am using the notation tau stands for R1 and C. Tau is R1 into C, and you have another notation here alpha, that is nothing but R2 divided by R1 plus R2, what you are having in the denominator. So R1C is replaced by tau, that into S plus 1 divided by 1 plus this is alpha into tau into S. And remember, alpha is R2 by R1 plus R2, and hence this value always it must be less than 1. So this is your transfer function in time constant form, and you can convert that time constant form into pole zero form the way I have explained in the control system class. And while taking the reading for this in experimental approach, since you have alpha here, the overall magnitude will be multiplied by alpha, which is less than 1, and when you convert this into magnitude by taking 20 log, you are going to get negative values for this, and hence once if you measure V0 peak to peak in the experimental approach, you multiply that V0 peak to peak by 1 by alpha, so that this alpha will get cancelled, and when you convert that into decibels, you will get only the positive values. So with this transfer function, let us see how the frequency responds in theoretical approach. Already you are familiar with the board plot. Replacing S by j omega, the transfer function comes like this. So in fact your transfer function is alpha into tau, S is replaced by j omega plus 1 divided by 1 plus alpha into tau S, and I am using here a Kc. It is nothing but, just now I have told that it should be multiplied by 1 by alpha. Here I am assuming that there is an amplifier with a gain Kc which is equal to 1 by alpha. So overall gain Kc into alpha is nothing but 1 by alpha into alpha. Alpha alpha get cancelled, means overall gain becomes 1 here. So you need to construct the table. You know how to construct this table. You have only 2 terms and the gain is 1, total 3 terms, and the respective corner frequencies. Initially you will have to find what is the starting point of your magnitude plot, that is the initial plot. So 20 log of k plus or minus 20 log omega, but in this transfer function you don't have any poles or zeros at the origin, so the second term in this equation does not exist. So it is 20 log and this value is 1 and hence it is 0. So the starting point is 0. Similarly, you write down the expression for phase shift. Then for the various values of omega, you calculate the angles. So if you plot it, your lead compensator plot comes like this. Initially, it will have low magnitude, very small magnitude, and at the corner frequency 1 by tau, it starts increasing with a slope of 20 plus 20 decibels. Then when it reaches another corner frequency 1 over alpha tau, again the magnitude remains constant. In fact, in our practical approach, output amplitude should remain constant from here to here, and here also start from lower frequency to this corner frequency, output should remain same, but between these two corner frequencies the output magnitude will increase. If you look into the phase angle curve, the maximum phase shift occurs at omega m, and this is the maximum possible phase shift which occurs between the output and the input. But for the lower range of the frequency, the phase angle or the phase shift between the output and the input is smaller than this. Even for the higher range of the frequency, it remains same. So the curve comes something like this. Start from lower frequency to your maximum possible frequency, the phase shift will increase, and after omega m again the phase shift will decrease, right? And this is how. So here remember, the phase shift or the phase angle is positive as it is a lead compensator.